Okay, 7:30. Good evening, all. Let's get started. Let me hit the record button for the cloud. Okay. All right. So now we are starting. Onto your next advanced architecture topic is the pipeline. And these 2 days, today and next day, we'll be spending time on that architecture to understand how it helps to improve the performance. Any question for you guys?
I have a couple quick questions about just finishing up with project 2. So first question is, with parameters, I was encountering a weird error where when the parameter in the memory file, the memory Verilog, and the DaVinci test bench Verilog were different. It was causing a conflict where if they had different values for the memory, for what they were loading in, I would get X's instead of the actual numbers. Do you know what was causing? What would be causing that?
I don't get your problem correctly. So it is loading that file?
I think it's trying to load both files. It's trying to load the file that was the parameter in memory and the def param in DaVinci TB.
It should not affect unless make sure in your DaVinci.tb you turn on only one file loading, not the both of them.
Yeah, I'm not. There's only one def param that's uncommented.
But yeah, otherwise you should not have a problem. At least.
Okay. Yeah, I was thinking that too, and I thought it was kind of weird.
No, something else is going on in that case. It's not even.
Okay. All right. The second question is, I was looking through the guideline for. Okay.
You lost your voice?
Yeah, no, I'm just thinking.
Oh, okay.
Okay, yeah. So yeah, okay, yeah. I was thinking of something else. So this question is a question. I know what's wrong. I just want to know how I'd go about fixing it. It's with the load word and pop instructions. I'm having a memory conflict where it's not loading the memory data during the mem instruction.
Okay, that's very specific to implementation. So
yeah. So what I'm thinking. So what I was thinking is either I like set the mem flags beforehand. So no way, I can do that. So I think I should push the memory load, the part where I actually get the memory data into the write back stage for those two.
Yeah, it should be coming in the if you send the memory instruction, like read instruction with the address set up at the previous cycle at the mem, at the end of the mem cycle, that is start of the write back cycle, you should expect your data is ready at that point.
Okay, so I should load in the data during the write back cycle.
Yeah.
Okay, got it. Yeah, in that case, I just mixed up a little on what the implementation was going to be. All right, so that's okay. So that's good. Anything else? I guess the last question is for taking screenshots of waveforms for this project. What exactly are you going to look for? Are you looking for just I take a picture of like one cycle where an instruction runs, something like that?
It's the other way. Like, let's say you are describing your testing and how you make sure your processor runs correctly.
Okay.
or if you followed any special debug process that you want to capture in the testing step. And
Okay.
that way, if a waveform helps you to explain it better, then include it.
Okay. I got it. All right. I think that's everything. Thank you.
Okay. How
Yeah.
about others on the
Professor,
project?
Professor.
Yes.
So for the project, what files do we submit? So we had to edit like the ALU, the register file, the control unit, and the test bench. So do we only submit those four? Do we submit any of the DAT files,
I
or do
also don't need test bench, but you can upload it. It's not no harm.
okay?
What we evaluate based on your ALU dot v, register underscore file dot v, and control underscore unit dot v. Those three files. Those are important.
So
Test bench in the important in the sense like let's say something like our testing shows some problem and you said, hey, I tested with my test bench, then I go look into the test bench and see what is going on in that sense. But I think you can supply that latter as well if those conflicts comes in.
okay, so
Mainly those three files. And okay, those are in the zip file, and of course your project reports is uploaded separately.
uh,
It's not a part of the zip file, but it's uploaded separately.
okay, so you're saying that we can submit the test benches if we want to?
Yeah. If you want to, you can submit. What we all do is basically copy from your submission those three files
Okay.
and put it under our testing environment and test it.
Okay. So we really don't need to submit like any of the processor.v file or like the
No, no.
.v. Just those three are the important ones. And
Yeah.
and optionally we can send in our other test benches too. Like if we
Yes.
have a test bench for the
Definitely.
register file, right?
Yeah.
Okay.
But you do say for sure the DaVinci test bench in the assignment page, because that's where we define like how we're calling our custom test if we have one, or how we actually.
If you have submitted the custom test in the package, yeah, submit the DaVinci.tv. What all I'm saying is that I don't evaluate on other files except those three files I mentioned.
Right.
So Professor, if we just submit those three files, we would be okay, right?
Yeah, we should be okay.
Okay, and DaVinci.testbench is not required, just the ALU, the register file, and the control unit.
Yes.
Okay, thank you.
I have a question.
Yes.
So the register file is 32 by 32,
Mhm.
and the top four, 28 to 30. The top four are those special reserved ones, program counter, IR.
Mhm.
So in our implementation of the register file, should we just only create one that's control 28, since in the control unit file there's those four or three rather, because we don't use the global pointer, but those three special internal registers?
As far as register goes, we should be able to access all of them, like those 32, including the special register mentioned in the instruction set. As you can recall, like in the assembly level programming, there is nothing called a special register. It is just by software convention. Those are used in specific purpose. Okay. So that means as far as the access of the register file goes, we need to be able to access all 32. That is number one. And number two, regarding the stack pointer, that let me especially note that down in a minute. But other than the stack pointer, there I think global pointer, frame pointer, those things are not actually used in this in the testing process or anything. We are basically testing through very simple assembly programs. So don't even worry about those other pointers. About the stack pointer, it is possible if it is also okay if we actually use a separate register storage and use that as a stack pointer. Remember in the data path discussion, we actually, instead of using the special register 29 for the stack pointer, in the data path, we actually use a separate register component there for just for a special purpose of registers. You can go through that route as well. Just have a special one storage for stack pointer. That means our register file has become truly general purpose register file. No special registers there. That's also okay. Okay.
Thank you.
Also, Professor,
Yes.
this is more of a theoretical question, but
Mhm.
are there, like, for this processor we're simulating, it doesn't seem like we have different data paths and control paths, because I thought like the data path was like the multiplexers and the circuits connecting to each other, and then the control signals are like the selection bit for
Right.
the multiplexer. But here is like combined. It's like the controller is the data path and the control path at the same time, because it provides everything.
Yes, so data path here in the broader sense consists of your ALU, register file, memory, right? And program counter as a special register and so on and so forth. So those are the main components, data path components. And in the behavior modeling, what we are trying to do here is basically to capture the control of those major components.
Yeah.
Okay, so that's why you see there is no separate data path as a module, and we are constructing multiplexer and everything, which will come in project 3 exactly. So we'll have a gate level implementation, logic gate level implementation of data path. And in that case, controller unit become purely a controller unit, which basically spit out the microcode for each stage of execution, okay, for the data path to control the data flow through the entire circuit.
Okay. All right. Thank you.
Okay, so conceptually, this project gives you like how things are achieved by synchronizing the operation between ALU register file and the memory, that aspect. And on the project 3, you will actually have this hands-on what exactly goes on at the logic level. So these are like two different conceptions that you need to pick up. And hopefully at the end of the project 3, the whole picture will be clear to you.
Thank you.
What else?
Professor,
Yes.
I just want to make sure, even though you're only grading those 3 files that we're submitting, I just want to make sure you want us to turn in everything though, right? With the work and the .mpf file, the project file and everything?
You don't need to. If you want, you can. They don't carry any extra points.
Why would we need to include the model sim project files at all? Like, how would that?
Yeah, because that would help me anyway. But these, if you want to turn in your test bench, you are welcome to do it. As I said, like if there is any testing conflict, then I usually ask that, hey, how did you test it? And then you forward me the test bench or any of your test programs. And then I compare it and let's see what's going on, right? It might happen that our test bench we have may have a problem, right? Like everything is bug prone. So that's why I want you guys to have the test bench ready in case there is a conflict of interest, and I can go back and look at your test bench and make sure what's going on.
But there's no harm in turning everything in, right? Because
No. We have a process to just cut out your 3 files from your submission.
Okay.
Use them.
Professor, quick question.
Yes.
I'm not sure if you addressed this previously, but for the purposes of like testing and for our report, for the testing part of our report, are we allowed to like share our DAT files with each other for testing?
Yeah.
And then we can cite that in our report or something like that, right?
Yes, you need to. Yeah, that's very important that you cite that, hey, you are people, the strategy and so on.
Okay, but as long as we cite it, it's fine, right?
Yes, yes. But
Okay, great.
yeah,
Thanks.
on the report side, I don't expect you have similar similarity score high with your groups because of the testing part, because that wordings has to be yours wording.
Yeah, and yeah, the wording is, yeah. Okay, that's fine. Okay, got it. Thanks.
Okay, so if there is nothing else, then I can let me quickly give you this overview. Okay, before that, why don't I just take a poll? Your class preparedness. Let's take a minute. Let's see how much you read.
Professor, I have one last question. So I'm getting an error, which is my port size does not match the connection size.
Oh, that's
And I
fine.
know why the error is happening. I know why the warning's coming
This is
up.
warning, basically, right?
Yeah, so I know why the warning's coming, but everything's working otherwise. So
Yeah,
it
this
should
is
be
fine.
fine, right?
Yeah, we know
Okay, perfect.
We're almost end of the poll. Okay, let me end the poll and share the result with you. So this is how it looks like. Oh, majority of the class haven't watched today's lecture, and the lecture note maybe is a better. Maybe I attribute that to your deadline for the project, but make sure you pick it up next day, please. Okay, so with that, why don't I just give you an overview of what is a pipeline and what is the strategy of that as today's discussion. So all we know that so far that we have this five-stage execution in our simple processor that we are dealing with in this class. We are implementing that also in our project, that we have these five stages, right? One is your instruction fetch, then it goes to, let's say, instruction decode, register fetch, then it goes to exe, then it goes into memory, then it goes into write back, and it cycles through like this. It starts from instruction fetch at the very beginning, and this state machine just per clock, it cycles through these states. And each state, if you see, each state is using some of the hardware component. Like this stage is almost related to your memory. Like instruction part of the memory is accessed and being ready. And whereas this part, instruction decode and register fetch, it is more utilizing your register file. It is reading from here. And exe is more related with ALU. This is utilizing that. And then your memory is, of course, it is related to the memory, but it's a data part. So this is the data memory, whereas this was the instruction memory. And write back is related to the register file. Now it is writing register file. So this is on a write into there, and this is more like a read. So you see, like at each moment, at each phases, it uses different resources. So that's the first thought process that, hey, like if I am done with an instruction one, fetch of that from the memory and send it to this next stage, then it is always okay to make the next instruction at this place. So let me just try to elaborate that. So let's say I am dealing with, in the first place, I have an instruction one came in. And when it is there, and it is then sent that instruction action related to that instruction and for the register read and everything, then that instruction is sent into the exe phase to involve the ALU to compute result. Then that instruction is sent to the mem stage to access memories, data memories if it needs, and then it sends to the write back stage if it needs to commit any result to the register file. So see, while it is in the write back phase, all other stages or corresponding resources practically are idle, right? So the idea is this, that when it sends this thing to the register fetch, I bring back next instruction from the memory. And, oh, sorry, not high 5, I2. And then when it goes into the exe phase, this guy pushed into the register fetch and I get another instruction from the memory, I3. And then I2 sent into the mem stage, sorry, I1, I2 into the exe, I3 pushed into the register fetch, and we can actually fetch one more from the memory, next instruction. Then I2 gets here, sorry, I1 gets there, I2 gets there, I3 is pushed into this, I4 gets into that, and next instruction, I5 gets here. And then once the write back stage is done, it's kind of thrown away, right? It is thrown away. So it's practically thrown away. So let me delete it. So I2 comes here, I3 comes here, I4 comes here, I5 comes here, and we do another I6. And at the end of this stage, I2 is thrown away, it's done. And I3 comes to the final stage, I4, I5, I6 up. And I7 is being fetched. So this is the concept of the pipeline. Through some hardware tricks and circuits, we basically try to achieve this. Like through each of these phases, we kind of trying to push the instruction so that you utilize the corresponding resource set at max. So that is the whole idea behind the pipeline. And this concept is not only applicable to this one. If you think, like for example, if you go back to your adder circuit, right? Your ripple carry adder circuit. Remember, like it has this daisy chained full adder, like let's say 4-bit. Full adder 0, full adder 1, 2, and 3. And your summation is being computed in LSB to MSB direction, right? Gradually. So that means we can further make it a pipeline process by separating the stages. And let's say this was when it was computing, let's say your summation for, let's say, function 1, okay, then it sends to here. And then this first adder, FA0, can actually start summation for next function too, right? And then it sends here, this summation sends here, and it can start, this LSB can start next function. So you see, like, these things also has a notion of parallelization through the pipeline that can boost up performance of the adder itself. So that's why I say, like, this pipeline is not just the sole concept within the processor itself, but we can apply the similar concept if we need to make like faster adder and so on and so forth. So that is the concept of the pipeline. Question? Okay, now next is that, as we saw that, if the instructions can be fetched like one after another and pushed through this circle of life, I would say, for this instruction execution, then it will gain like 5x speed up, right? But why cannot we actually gain 5x? There comes this different type of hazard, like structural hazard, data hazard, control hazard. Structural hazard, for example, like when, for example, when your I3 is actually trying to write into the register file, I6 is trying to read from the register file. So they're using like the same resource. So that's a structural hazard. Similarly, while we are trying to fetch I7 from the memory device, instruction part though, I4 may be trying to write into that memory, right? Different location, but at least resource, hardware resource, right? They're the same resource. So these are the structural hazard happening. And we need to resolve that before even going to the next type of hazard called the data hazard. So we have this structural hazard. So one is structural hazard. So this lecture dealt with that one. Then we have data hazard, I'll come to that. And then we have control hazard. Okay. So structural hazard, we need to resolve hardware, and please look at the lecture. It talks about how we can deal with those kind of structural hazard. Now about the data hazard is more like a data dependency. Let's say I6 is accessing a result which should come from the I4, let's say. It should come from the I4. Now you see, like, for example, let's write down a little bit of code here. So let's say I4, it was something like add R3, R1, R0, and whereas I6 is add R4, R3, R10. You see that result of I4 is used in the instruction I6. That means when I6 is accessing the register file, it expects that R3 is updated with the I4 result from the instruction 4. But look at the instruction 4, it's still in the memory, it didn't commit it back to the register file yet. So that means at this point, instruction set 6 is accessing whatever that registered value is wrong. It's probably coming from some other previous instruction, like maybe from at this point, instruction 1 was add R3, R4, R5. So it is practically accessing result of these guy instead of result of these guy, right? So that's the data hazard. We need to make sure somehow we need to resolve that hazard. And for that, one obvious step is to delay I6 till a point I4 goes into the write back. So what happens here? One thing is like this is done. This I4 came here. I5 came here. But we don't send I6 right there, right? We keep the I6 keep waiting. So this become your bubble state or null state. So this is something called inserting a bubble in the pipeline, that we are keeping the I4. And once the I4 is done, okay, then I5 sends here. Then I6 is sent here and I7 is sent there and I8 is fetched from the memory. So you see there is a delay induced here to make sure there is no data hazard, and that of course will affect your performance. Now in this case, instead of 5 cycle, it suddenly need a 6 cycle, one extra cycle there to get it done. So that means it is decreasing the performance right there. And there will be many such dependence cases, instruction in a program. And that's why it cannot achieve, that is one of the reasons it cannot achieve this full potential of 5x speed up. Question so far? Hey, I have one from chat from Mary. Is there anyone else not able to access files, videos in module 7? I don't know. Is there anyone else who has the same problem? Cannot access files or videos in module 7? Maybe Mary, you need to actually watch the previous module, all of them complete. If you only after that it will unlock module 7 for you. Maybe that's happening for you, if it is not a problem for others. Okay. Now about the control, like control hazard. Now what is that hazard is? Let's say in a program, my instruction is this. BNE, if R2, R1 are not equal, then jump to L3. L3 is something, let's say R10 is R10, R8, something like that. And we have some more in between, some add, some subtraction, etc., etc. Doesn't matter. Now the matter is this. Let's say this is my instruction 8. Okay, let's to understand that part. Delete. Okay, let's say this is my instruction 8. Okay, this is my instruction 8. This is my instruction 9, and this is my instruction 10. This is my instruction 11. Okay. So this is more like a situation where we need to decide if the branch is taken, versus the other path, the normal path, which is coming from here to there, branch is not taken. Okay. Now let's say I8 is my BNE. We fetched it. That means in the pipeline, let's say we expect sorry, 7 duplicate I6 duplicate I5 duplicate I4. So they're in the pipeline. Now, now we are done with I4, I3. We're done with that. I5 goes here, I6 goes here, I7 goes here, I8 goes here. And now question is, which one should I fetch? Because you see, depending on this comparison result, which is not done yet, it will be done in the exe phase. Only after that comparison is done, this instruction will, or controller will know whether to fetch next instruction is instruction 11, that is branch taken, or instruction 9, right? So what we can do here, here's a dilemma, and we need to go either way. So let's say it did decide that it predict that branch was taken. Okay, branch was taken. So it predict that, and with that prediction, it basically picked up instruction 11 from here. Okay. Now I5 is done. Instruction 16 is in pipeline. Instruction 7 goes here. Instruction 8 goes here. Instruction 11 goes here. And of course, the next one would be instruction 12, right? As a next instruction of that. Now, at the end of this story, now we know, like once it is done and is moved to here, this move to there. At this point, we know that, and also like, let's move this guy to here, that guy to there. Now I know, let's say in this case, my case was branch was not taken. In fact, my next instruction should have been I9 instead of I11. So what we do here, what we do in this case, we basically purge the pipeline for 2 cycles, okay? 2 cycles. So what happens is that we let this happen 1 cycle. Next cycle. Wait a minute. Oh, no. Wait, just hold on. I'm just mixing up things here. Sorry for that. So in this case, what happens is your this guy is purged. This guy is purged from the pipeline. Okay. And a bubble is inserted or null. So no action happens in these two. And your I9 is fetched. Nine is fetched. And now the things goes on as it is. This is done. This one is done. I8 move here, bubble move here, another bubble move here, I9 comes here, then I10 comes there. The next cycle, I8 is done, bubble is moved, I9, I10, and it's duplicated. I11 from the memory, then this bubble is purged, this bubble comes, I10, I11, duplicate, I12. Now this is purged. Now pipeline is in a good shape without bubble. So I9, I10, I11. So you see that we introduced two bubbles, or that means two cycle is lost in this situation. And that's what is called a control hazard. Means there is an indecisiveness with each of these control BNE, B equal, that kind of instruction, that a pipeline processor need to decide which one to predict, right? In this case, prediction was wrong. That's why we need to add the bubble. But if the prediction was right, then there was no point, there was no cycle miss during that during this prediction operation. So this introduces you another set of delay or delay in the cycles, or it consumes the cycles through the bubbles. So that's what reduces down the performance for achieving till 5x in this case. Question? Okay, one more thing I need to tell you. If you go through this, how this register file is the structural hazard is resolved, is basically we did a parallel read-write feature. So this hazard is structural hazard, parallel read-write. In register file. So that resolved my read and write at the same time during different phases. And the memory, that conflict between the mem stage and instruction phase stage, these two stages, was done by separating out the memory, data memory and instruction memory, and somewhat followed like a Harvard architecture. In fact, this architecture, actually we have a mix of von Neumann and Harvard in this case. So what we introduce here, yeah, let me just remove this part quickly. Okay. So here's a controller, let's say processor, or controller, I would say. What should I say? Processor. Okay. And von Neumann architecture says there is a single memory. What we do, we basically introduce an intermediate instruction memory and data memory. Instruction memory and data memory separate. So this part is your Harvard architecture. Whereas this part, whole system, is still a 1 Newman. Okay, and your data flow to and fro from the main memory, this is now we call it a main memory, to the instruction memory and data memory, and processor individually interact with them. So from processor viewpoint, there is no one single memory called main memory. Now it is divided into two separate memory, instruction memory and data memory. And we'll see in the next, actually the major module, memory hierarchy study, we call it a cache memory. C-A-C-H-E, cache memory. So this entire thing is called a cache memory, and all modern processor goes with this cache memory. It's not only for the pipeline support, but it has other advantages we'll see in the memory hierarchy study during the end part of this semester. But this is what the cache memory is, that whatever you hear when you like try to buy a desktop or a laptop, you look at the memory, the main memory is this, and this much cache happens in the processor. That's the cache memory they talk about in their laptop spec or the desktop spec or in general in the processor spec. And this cache memory usually go in the same silicon as in the processor. So we get a like Intel Pentium chip or i7, Core i7, etc. And those chip has this register file, control unit, ALU, etc. And also it has a major part of the instruction memory and data memory, that cache memories. In fact, if you look under the microscope, the different areas, biggest area nowadays in the whole processor is the cache memory. Whatever you are seeing, most probably you are looking at a cache memories there. Okay, control units and takes so much little space. Its major dominant space is occupied by the cache memories in the modern processor. Question? Okay, if there is no question, then let us close tonight a little early and make sure you submit your project 2 as deadline specified and move on to the project 3. By the way, this week we are restarting the labs. It is all about the gate level modeling, and each lab gives you some task which is basically part of project 3. So don't miss out on those labs. Okay, like whatever they ask to do, please do it. Make sure you do it so that you are on track for the project 3. Question? Yes,
Professor, I have a question on the state machine.
Mhm.
So I've done a lot of test files, and I think all my instructions and everything in the CPU works. But for the state machine, like the initial state, for me, it started at state equals proc fetch. But I saw that in your project guide, it was supposed to start at an unknown value, and the next state would be the proc fetch. But in my waveforms, when I look at my waveforms, for the initial value for I'm not sure why, but even when I set the initial block to state is equal to unknown value and the next state is equal to the proc fetch, in the first waveform, I saw the state was proc fetch instead of the unknown value. So does that really affect anything?
As long as it works, that's fine. That should be okay.
So as long as like the entire computer works?
Yeah.
Okay. All right. Thank you.
I had a question about the deadline for the assignment. The actual assignment, like it says that it's due midnight, but it's available until 6 a.m. Does that mean that 6 a.m. is like a late turning time, or is that like
Late turning time, yes, it's still open that like a late, but it has a penalty. I think as far as I remember, it has been set to 5% per day. That means if you go over 11:59, 5% will be deducted.
Okay.
You can still do it if it makes sense, like for you to take 5% deduction and still get you higher grade than what it could have been done by 11:59, then that's probably okay to do.
Okay. That makes sense. Thank you.
Professor?
Yeah.
I have a quick question.
Mhm.
So do we need to submit the test bench for the ALU and the memory file?
No.
Optional?
Yeah, we just discussed that the beginning of the class, that you don't need to, you can, but you don't need to.
Oh, okay, so we also don't need to mention that in the report, right?
You still, yeah, because that is a big section for the testing. You need to mention how did you test your implementation.
Okay, thank you.
Okay, any other thing? Okay, then good night all and see you on Wednesday.